Welcome back to physics, everyone. We are going to start a new topic, momentum and impulse, and so let's get started. All right, so what exactly is momentum? Well, let's just briefly revisit what we've studied so far. When we talked about kinematics, we used kinematics to define various quantities we associated with motion, such as displacement and velocity and acceleration. And we've gotten quite good at computing those quantities and figuring out how things change in a motion problem. Then we used Newton's laws and the idea of forces to explain why motion changes when a force is applied. Well, what we're going to do now is use the concept of momentum and its related sister concept, which is impulse. And momentum describes for us, and let me grab myself a pen here. So momentum describes for us how the force and the time of contact between objects affects their motion. Get this written in. So when we talk about momentum, we're focusing on force and contact time. Okay, so how do we calculate it? Because of course in physics we're always looking to calculate things. Well, momentum is pretty simple. It's just the product of mass and velocity. And in equation form, you can see it's written there. The symbol for momentum is a p, usually a lowercase p, and it's equal to mass times velocity. And notice that the p is in boldface type and the v is in boldface type because momentum is you got it, it's a vector. And a vector, of course, has both magnitude as well as direction. So when we talk about momentum, we're talking about something that has both a numerical value associated with it as well as a direction. And of course, looking back at the equation, where is it going to get its direction from? It's going to get its direction from the velocity. Units are pretty simple. They are taken simply from the quantities you use to calculate momentum. Mass, of course, is going to be measured in kilograms, and velocity is measured in units of meters per second. So the units for momentum are simply kilograms times meters over seconds. So quick and simple example, we've got a 2,250 kilogram pickup truck. Its velocity is 25 meters per second to the east. What's the momentum of the truck? Well, we go back and we look at our equation. Momentum is equal to mass times velocity. And so this is a pretty simple case of just substituting in the values. I've got 2,250 kilograms is the mass of the truck. The velocity is 25 meters per second. Come on, work. 25 meters per second. And when we plug and chug, we come up with a value for the momentum equal to 56,250, and the units would be kilograms times meters over seconds. Now it did say what is the momentum, and of course we remember that momentum is a vector quantity, so we go back to the context of the problem to figure out what the direction would be. Since the truck was initially moving with a velocity in the eastward direction, our momentum is also going to be in the eastward direction. So there's our answer. Okay, well, let's revisit Newton's second law a little bit. To cause a change in momentum, it takes both force as well as time. That force has to be applied for some interval of time, whether it's short or long, in order to cause a change in momentum. Well, we know Newton's second law. Up to now, we've always said net force is equal to mass times acceleration. Let's make these vectors. But originally, Newton's second law was written this way. Net force, and it was a vector, is equal to a change in momentum over a change in time. Now, if we rearrange that, we could rearrange it and multiply both sides by that time interval term. And so I would get net force times the delta t for the time interval is equal to the change in momentum of the object. And this term, net force times delta t, is called impulse. and it's represented by the letter J. Now we're going to look at some of the implications of that because it has some pretty interesting implications that we use and we rely on every day for our safety and just for general things that we do without thinking about them. So what are the implications? Well, a net external force applied for a period of time is going to cause a change in momentum. So if we think about this in equation term, and I like to use the phrase or the idea, let the math talk to you. So let's write out that what that equation we just wrote down was, and we had force, and this would be the net force, times the time interval is equal to an object's change in momentum. So let's think about how that's applied in airbags for cars. Over here to the side, we've got a picture of a crash dummy who is has an airbag that has deployed, and of course the face of that crash dummy, as you can tell, is going to go, bang down into that air pillow that has been created when the airbag exploded out of the steering wheel. Well, what's the point of that? Well, think about it this way. If, for instance, this car has crashed into something, so it has gone from some initial velocity to abruptly being stopped by either having a head-on crash or by, with another car, or maybe into some object like a telephone pole or a side of a building. And of course, airbags are designed to explode, to actually deploy when you have a head-on crash. Well, how does that help the driver? Well, let's think about it. The change in momentum of that car as well as that driver is going to be equal to the change in the mass and velocity product of that car and that driver. Well, primarily we're thinking that mass is not changing, so it's the velocity that's changing. The velocity is abruptly going from some initial value to 0, for instance. And that's going to be accomplished through the application of a force for a certain period of time. Well, if this quantity is constant, in other words, you're not really losing mass and you've got a given change in velocity, then you could accomplish that one of two ways. You could either have a very large force and a very short time. Okay, that's what would happen if this airbag were not present in this picture. So if the airbag were simply taken out of the picture and the driver's head impacted the steering wheel or the dashboard instead, then there would be a very short period of time and a very large force. Well, can you imagine how that feels to the bones of the face? Obviously, it's not a good thing. However, let's see, can I go back and pick up an eraser here? Let's go ahead and erase the X's that I put through the steering wheel. So if I keep that airbag in place, then here's what's going to happen this time. Now that driver's head, instead of impacting a very hard surface, it's going to impact a surface that does have a bit more give than a steering wheel. So now what happens is that instead of slowing down, just bam, hitting the steering wheel, the driver's head is going to deploy and slow down at a slightly longer time period. So we've extended the time over which the velocity of that driver's head comes to a stop, and that means that the force that it takes in order to accomplish that is less. So I don't know how many of you have actually had an airbag deploy on you. I've heard, thankfully I have not. I've heard people say that you do get some, you can get facial burns from like rug burn type things, but compared to breaking the bones in your face and having to have plastic surgery to reconstruct the bones in your face, a few rug burns is probably a really good trade-off for that. Those of you who are athletes and play any kind of sport that involves balls or rackets or just catching, throwing, etc., know that your coach always tells you to follow through. And why would that be? Well, the longer, again, for a given change in momentum of that ball, it's accomplished through the application of a force through a certain period of time. Well, let's say whatever force you apply is a given value. If you stay in contact with that for a longer period of time by following through, then for a given value of force, the change in momentum of the object is going to be larger. So this is what I mean by letting the math talk to you. Let the, if you keep one quantity constant in the equation, then you can look at the effect of changing another quantity and how that would affect the overall problem that you're studying. Okay, so let's apply this and do some computations. We've got a 1,400 kilogram car that's moving to the west, and its initial velocity is 15 meters per second. It unfortunately hits a tree and is brought to rest in 3/10 of a second. What's the magnitude of the force exerted on the car during this time? Well, let's see. What do we know here? Here, the 1,400 kilograms gives us the mass of the car. 15 meters per second gives us the initial velocity. And then brought to rest, right there gives us the final velocity. And then 3/10 of a second is our time interval. And what we're supposed to do is find the net force exerted on that car. Well, your physics brain at this point might say, oh, well, okay, net force is mass times acceleration, and I've got enough to compute the acceleration of the car and just multiply by the mass. Well, yeah, essentially you do. And when we're doing problems like this, we're really using that and using the idea of momentum and impulse here to help us just expand what we already know how to do and learn to use it in different ways. So let's do it this way. We know that net force is equal to, in this case, that change in momentum over the change in time. So let's come down here and calculate it. Net force is going to be equal to change in momentum. Well, the mass of the car is not changing. So I'm going to factor out mass and say it's mass times change in velocity over the time interval. So mass times final velocity minus initial velocity over the time interval. Whoops. And the final velocity was 0 because it was brought to rest. So we've got mass, which was 1,400 kilograms, times the initial velocity. Notice it is a negative because of the final minus initial there, times the change in time. And I'm probably not going to have room to write this, but we're going to end up with 1,400 kilograms. I'll try and keep it tiny. Times, we'll squeeze it in over here, minus a 15 meters per second. And we're multiplying by that. So let me put that in parentheses. And then divide by our time interval, 0.3 seconds. And we end up with a net force of 70,000, and it's negatives, minus 70,000 newtons. Okay, that's a pretty large force. If you think about what your weight is, you probably have a weight in, mass times acceleration. So approximate the acceleration due to gravity is 10 meters per second squared times your mass, which is probably about 50 kilograms. So you might have a weight of somewhere in the neighborhood of 500 newtons. So think about 500 newtons. I mean, if somebody your size jumped and fell on top of you, that would not feel good. Well, this is a force of 70,000 newtons. This is why airbags are a really good component and certainly a good safety feature for cars. Okay, so let's think it through. Stopping distances depend on momentum and impulse. Let's assume a car and a truck's braking system can apply the same force to slow the vehicle. If the truck's mass is twice the car's mass, how will the stopping times compare? Okay, well, let's see. Let's start with our equation, and again, let's let the math talk to us. I'm going to start with my equation that was change in momentum over change in time is equal to the net force. And I'll tell you what, let's go ahead and get the time term isolated. So if I do that, I get time is equal to change in momentum over net force. So let's do a comparison then. The time interval involved here is going to be equal to mass times the change in velocity divided by the net force. Well, let's see. We're coming to a stop, and if they were started at the same speed, so we'll say the change in velocity is the same for each, so this term is constant. The truck and the car's brakes can apply approximately the same force, but the mass of the truck is larger by 2. So if I multiply that by 2, that means this time to stop is also going to go up by 2. So think about that. If you've got a big truck coming up behind you and you can see you might need to stop, you know, it might make sense to maybe change lanes if you have that capability to do so. Let's think about a second part of that, or a follow-on. If both the truck and the car were traveling 30 miles per hour initially, how would their stopping distances compare? Well, in the last part, we figured out that the time for the truck to stop was twice as much. So how would that impact this situation? Well, if they were both traveling 30 miles per hour initially, and it takes the truck twice as long to stop, then that would logically imply that the stopping distance is going to also be larger. This is why in the driver's ed book, it talks about stopping distances, but it gives you a little, just a kind of a rule of thumb that here we can see that it takes a different distance for a truck and a car to stop. However, in the driver's ed book, it doesn't, give you what you have to memorize for a truck versus a car. It just gives you kind of a rule of thumb that's good for any mass of a vehicle. And that is, if you follow behind somebody, there's a 2-second rule. You ought to give yourself at least 2 seconds time behind them, if at all possible, so that you will have time to stop if they suddenly come to a stop. So, driving on the interstate, pick some landmark, a sign post or something like that. And once you pass that, once that car in front of you passes that, count 1001, 1002. If you've got at least 2 seconds of stopping distance, then you should be okay should you have to abruptly stop. All right, so wrap it up. Momentum, we've learned it depends on mass and velocity, and it's just a simple product of the two. It is a vector. Units are kilograms times meters over seconds. To change momentum, it requires a force, and it also requires contact time. The longer the contact time for a given force, the bigger the change in momentum is going to be. Impulse is a term we use to describe the product of the force and the time interval. And a given change in momentum can be accomplished one of two ways. You can use either a short time and a large force, or you can use a long time and a smaller force. And of course, if you want to be safe in a vehicle, or you want to drop something safely, for instance, or just, be comfortable, then you want a small force applied over a long time. All right, see you next time.